Hello and welcome to this Riviera-PRO demonstration. My name is Brandon, and today I'll be going over the QEMU interface for Riviera-PRO. To begin, QEMU stands for Quick Emulator, and as the name suggests, it is an emulator as well as machine virtualizer, supporting many different architectures such as x86, MIPS, ARM, and more. QEMU is free and open source, while also providing near native speeds, making it an ideal platform for anyone wanting to try out different machine architectures, or wanting to test on those architectures. In fact, that is what I'll be showing today, as QEMU will be used to emulate the ARM Cortex-A9 within the context of this demonstration, and will thus act as the virtual processing system of my Zynq-based design. Now, the design itself is just a simple PWM IP, which will be ran as RTL within programmable logic. To simulate this component, we will be using Riviera-PRO. This tool will provide the hardware debugging capabilities, such as logged waveforms and hardware breakpoints, similarly to how QEMU will be providing the platform for our software component of the design. Using both tools, that is Riviera-PRO for the programmable logic and QEMU for the processing system, along with the Aldec QEMU bridge between, we can fully model a complete Zynq SoC, allowing us to perform powerful co-simulation of our design. Here, the hardware component will be simulated by Riviera-PRO, while the software component will be ran on an emulated ARM processor within QEMU. This software component will control the PWM IP, allowing it to modify the signal's duty cycle, with those transactions taking place via the Aldec QEMU bridge. The major benefit of such co-simulation is an accelerated verification process for complex hardware and software interactions, as accompanying team members in hardware and software can work together at an earlier stage of development. Additionally, with both domains being co-simulated, the debugging capabilities of Riviera-PRO and accompanying software debuggers, such as GDB, can fully interact with the complete design, all before putting anything on an actual board. That is, Riviera-PRO will be used to debug our hardware component, while software tools can be used to debug the software side, all without having to modify our design or test environment. So with that, let's go ahead and get into the actual demonstration. To follow along with this video or the accompanying setup guide, you will need a Linux host and you must possess a 2017.10 or higher version of Riviera-PRO, as well as QEMU itself. The actual process of setting up and building the project simply requires downloading QEMU and compiling it along with some demo files, and then running a few provided scripts. For a complete in-depth guide on how to set up the environment, please refer to our accompanying guide on the matter. For now, however, I want to show off the actual process of co-simulating a design. So once you do have all the required software and environment set up, we can begin running the project by calling from the demo directory either Start Co-Simulation 64 or Start Co-Simulation 32, depending on your system architecture. This will open an instance of Riviera-PRO with our PWM project open, as well as open these two Xterm windows. The first window has an instance of QEMU waiting for the Aldec QEMU bridge, while the second window is where we can start that bridge. With our PWM project now open and our tools primed for co-simulation, we can now run our macro within Riviera-PRO to initiate the simulation. This script will go ahead and run the design, and once completed, simulation will begin. We can verify this by observing the simulation timer starting. And once it has start, we can navigate back to our second Xterm window and initiate the QEMU bridge by running the relevant launcher for our processing system. In this case, it is that for the Zynq 7000 series SoC. Once initiated, we can see in our second window that the QEMU interface successfully connects, and a new instance of Linux will begin to boot up within the emulator. Once Linux is fully up and running within our emulated processing system, we can then begin to utilize it and run the software side of our PWM project. This will provide an interface for controlling the hardware component's duty cycle. So let's go ahead and change it a few times. The PWM will initially be off, so we'll first set it to 50%, 75%, and then finally 100%. After providing our example stimulus, we can end the co-simulation by typing Q within the second Xterm window. Once ended, Riviera-PRO will also cease simulation and our resulting waveforms will be available for analysis. Zooming into the time we initiated the emulator, we can see how the output signal reacts to what was provided from the software side. Our signal started at a 0% duty cycle and was changed to a 50% duty cycle. Zooming out and navigating to another transaction, we can see that final transformation of the output signal from a 75% duty cycle to a complete 100% duty cycle. Overall, we were able to control our simulated hardware using controls from our emulated environment. This was only possible with Aldec's QEMU bridge, which provided that means of early and simultaneous testing of hardware and software components of the design. So with that, be sure to check out the feature in Riviera-PRO as the solution for your co-simulation needs. And of course, thanks for watching.